Okay, this is a quite interesting problem. So here we have a balance. One side of the balance contains mass that is weight to balance this. There's one another side you have a solenoid. And this solenoid has n number of turns. And cross-sectional area of solenoid is S. So what you have been given? So there is a solenoid, something like this. So you have a solenoid. And the cross-sectional area of the solenoid is given to you, that is S, and it has total n number of turns. So it has n number of turns. Another side you have, initially there is a weight that balances the solenoid. So because the solenoid will have some mass, this is balanced by another mass, this side you have, that is a weight is, and this length OA is given to you, this length is L. So length OA is L. Now there is a current that is passed through this solenoid. So the current is passed through this solenoid. Then I have to put an extra weight to make the system stable. This means if I want to reach the equilibrium position, again I have to add extra weight if there is a current inside this solenoid. And this extra weight is given to you, that is delta M is the extra mass. So delta M is the extra mass you have here. Second time you have to put this mass. So this is extra mass. Are you getting? And we have to calculate what is the magnetic field B, magnetic induction. What is the B value here? So we have to calculate what is the B. So let me explain this problem. So what you have, this side, one end of you have solenoid. So there is a solenoid you have, and this solenoid is basically fixed by the balance one-sided. So this solenoid is basically not a, it's connected by a rod, and this rod, this side you have a weight that is connected by this side. So you have this side a weight connected this side. So let me see again. Yeah, this is the diagram. So you have a weight connected this side. So there is a weight connected this side. And you put some weight to balance this one. So now this is balanced. So initially system is balanced. So this is your axis about which it can rotate. Now there is a magnetic field. And the important point we have, magnetic field is something like this. If you see from top, it will look something like this. It's a north pole and this is your south pole. So this means the magnetic field here you have something like this. So this is your magnetic field direction. Are you getting or not? So this is important part we have. This is the only important part we have in this problem. So this is your north-south poles that is kept here. So this is the south pole, and this side you have north pole, and that is kept, and you have a magnetic field in this direction. Now current passes through this one. So if there is a current, there will be a torque. Now I know the torque is nothing but mu cross B. This is the torque, we know, mu cross B. Let us say magnetic field in this region is B. What is the direction of mu cross B? Mu is nothing but I times N times A, and is the number of turns cross B. What will be the direction of area vector? So if the current goes in this direction, either I will have area vector in this direction or in this direction. If I have area, so let us calculate what should be the area vector. So this is my B vector, and if I consider this is my area vector, so let us say this is my area vector. So what is A cross B? So if you have A cross B, so if you A cross B, if you see A cross B, this is coming upward. So this comes, this is the direction of A cross B. So this means if we apply a current through the solenoid, this will lift up. If this lift up, then there should be a reduction of weight, but we are saying there is a gain in weight. This means my area vector should be opposite. So I should have something like opposite. So this is my B vector. So this is my B vector. But my area vector should not be this. So this is not my area vector. I should have area vector something like this. If my area vector is this, now I can have A cross B. So this will come downward. Are you getting or not? So you can have, this is my A cross B. I cannot have area vector in this direction. So this means now I know the direction of current. So when you have area vector something like this, you have a solenoid. So let us take one turn of solenoid. So this is one turn of solenoid. You will have area vector. You want area vector in this direction. So this means if you follow right-handed rule, current should be something like this. So this is the direction of current. Are you getting or not? So what is the torque? So if the current is this, I can calculate. So then I need extra bit, because there is extra force that is acting on this solenoid, extra torque that is acting on this solenoid. So this is the tendency to roll this side. So I have to apply extra bit. Extra torque applied by the solenoid is this. So what is, I can say, extra torque. So I will have extra torque. So extra torque is what? So this is extra torque. So this has to be, this is NIAB, because A and B are perpendicular. So this is area vector, this is magnetic field vector perpendicular, sine 91. This is simply NIAB. So this is extra torque. Now to balance this torque, I have to apply extra bit. This is extra torque due to the solenoid. So this is this side. Are you getting or not? Now I have to apply extra bit. So let us say extra bit is delta M. So what is the torque? So that's the delta M into Z, that is the mass is delta M extra mass, then delta mz extra bit. What is the extra torque due to the extra mass? This length is L multiplied by the mz. So I can say extra torque due to the bit. So I have to multiply this extra torque due to bit. Are you getting or not? So this will be equals to, I have to have delta mz, g is gravity, and this multiplied by length L. Are you getting or not? And we have to, you see this torque is in this direction. So I have to create these two torques, NIAB. This is equals to delta M into Z into L. So I can calculate from here what is the B. So B is nothing but delta M multiplied by Z multiplied by L, and this divided by I times A times B. I have to have N also. So number of terms will also come here. And in the question, area is written as symbol S. So I can write this becomes delta M Z L, and this divided by NI SB. So this is a simple experiment. You can calculate magnetic field just by changing the bit. So you have two magnets. So one side of the magnet. So you see, you have two magnets. This side you have one magnet. Other side you have this magnet, North Pole and South Pole. If you want to find what is the strength of this magnet, this can be done using this kind of experiment. This is a simple experiment. You have a balance. One side of the balance contains a solenoid, initially no current. So the mass of solenoid is balanced by the mass of counter bit. Now next time you put the current inside the solenoid, as soon as you put the current inside the solenoid with proper direction, there is a force in the downward direction, or you can say there is a torque that is acting in the opposite direction. And to balance this extra torque, I have to apply some extra mass. And if I add some extra mass, that will also have some torque. Now if I equate these two torques, that is clockwise torque as anti-clockwise torque, we will get the magnitude of B. So that is the, I have two magnets. Now I know what is the strength of this magnetic field due to this magnet. This is a quite good experiment.